So, welcome to these lectures where we are reviewing our concepts that we have been utilizing all through this period for understanding how you are able to implement the quantum computing aspects. So, in doing so, we are going back to the problems that we had given to you, and based on their solutions and the understandings, we are going ahead with our implementation problems. So, once again reviewing, let us see where we stand as of now. In these reviewing concepts that we have been doing, let us look back to week 2, which we have been doing earlier, and in this we have been analyzing the problems that we have been doing there. We have finished 4 of them earlier. So, let us look at the 5th one, where it was looking at the concept of the orbital. Now, in the principle of analyzing the orbital, the question which was probing was to see how the node in an orbital is understood. So, the question essentially asked as to what a node of an orbital represent, and so it is a point or a plane wherein the wave function changes sign. That was the solution given. So, let us revisit the concept of the orbital and its nodes. So, in order to do that, let us look at the simplest of the orbitals, which is the s orbital, where the s orbital wave function has the form where the radial part corresponds to the distance, the angular part corresponds to this. Now, the angular part for the s orbital, as we know, is constant because there is no change along the is spherically symmetrical. So, the angular part is going to be constant. So, we get a spherical. There are 3 possible representations that are possible for looking at these orbitals. One is to look at the probability along the different axes, another one is to look at its contour along the 2 dimensions, and finally, it is to look at the probability density in terms of dots or colors. So, generally speaking, wave functions and orbitals are defined by their quantum numbers L, by their quantum numbers n, L and m sub L. Orbital is a wave function. It is a region of space where the electron exists, and it has energy, shapes and orientations in space. Thus, an orbital is defined as one electron wave function. So, here are the 3 s orbitals, which are all spherically symmetric, but as you can see, the sizes, shapes and orientations of the orbital depends on the quantum number. So, n determines the size, L determines the shape and m sub L determines the orientation. So, given the nodal plane as we show here, the orientation and the presence of this system is being shown here. Now, the px, py, pz are the ones which have angular dependence. So, they are non-symmetric along the nodal plane, whereas in terms of the s orbital they are always going to be symmetric. However, nodes can exist irrespective of the symmetry and other issues. So, in terms of s orbitals, the nodes exist in the radial part. So, 1s has no nodes, 2s has 1 node and 3s has 2 nodes. So, typically in terms of these are radial nodes which are represented in terms of n minus 1 kind of nodes that you will always get, and so the first one 1s does not have any node. Nodes in the p orbitals are of different kind because they are angular nodes that passes through the nucleus, and the orbital therefore becomes a dumbbell shaped because it is no longer symmetric. And in this case, it is important to note that the plus and the minus sign is shown, that is shown for the p orbital, refers to the mathematical sign of the wave function and not anything to do with the electric charge, because we are essentially looking at only the electron. So, there is no charge aspect associated with it. It is the mathematical sign of the wave function. It is something to do with the symmetry of the system. The nodes in the orbitals, for example, here we show the 3D orbitals. There are two angular nodes that pass through the nucleus. The orbital is 4-leaf clover shaped, and the d orbitals are important for metals and so on and so forth. But generally speaking, these are some ways of how to visualize these orbitals and to know that these nodes are the places where the sign changes are occurring, or the symmetry aspects are changing as you go across in terms of the orbitals. And that is why these are important in terms of the nodes and how they are represented in each of these representations. So, with that, let us now look at the case of the Schrodinger equation, which in terms of more than multi-electron system, it is known that it cannot be solved exactly, and the critical problem for that remains in what form was the question, and the electron-electron repulsion term has been pointed out as the main issue. So, in order to know this, let us first look at the helium atom picture and understand that it has one nucleus with 2 protons and 2 electrons. So, there is a 3-body problem, and so the 2 electrons can exist around the nuclei in 2 different directions, which gives rise to this condition where we have 3 coordinates to worry about, R12, R1 and R2. The state of the electron is given by the wave function, which depends on R1 and R2, and the potential energy is a function of both R1, R2 as well as R12. So, the kinetic energy or the center mass of the system would be also dependent on 2 of them, but the potential energy part is the one which has the difficulty, because the electron-electron repulsion part is dependent on the R12 coordinate, which is the one which is a coupled coordinate system in this case. So, if you write the Schrodinger equation in this form, the complete Schrodinger equation, it turns out that it depends on 3 coordinates here, R1, R2 and R12. And because of the last term, which is coupled between R1 and R2, the coming from the potential energy, the potential is anemospherically symmetric, and it depends on the angle between R1 and R2, and so the Schrodinger equation cannot be solved analytically. So, the way this has been looked at is to, so the way it has been looked at, this has been done is to approximate the problem, and that we will deal it later, but generally the Schrodinger equation has the electron-electron repulsion term, which needs to be taken care if this has to be solved. So, that was the part of the question which was asked. The very next question, however, asks about the electronic Hamiltonian of the helium atom in atomic units, which means that all the aspects of the mass and those are all taken as unity in terms of the atomic units, as we know. So, it simplifies and becomes a form which only depends on the differential parts as well as the distances, and so this is the actual form which I just showed you earlier in atomic units in terms of the Hamiltonian, and that is the one which has been shown here. So that there is nothing more to discuss in that. So, we come to the next question which was asked, which is the electronic wave function of the helium atom in its ground state. Now, this is under some approximation, as I have been discussing when we looked at the Hamiltonian before, that we can only solve this under the condition that we assume that the R12 term is not going to create a problem. So, let us look at how this is done, and the approximate model essentially is a idea which is assuming that it is an independent electron approach. The electron-electron repulsion term is going to be ignored, and so then the product of the 2 functions can be used, as then the problem essentially depends only on R1 and R2. The Schrodinger equation is then separated into 2 equations, and each one of the electrons in the helium atom is independent of each other. Now, this is an approximation, as I have been mentioning, because there is an interaction between the two electrons, but the interaction is as a first order level it can be ignored to at least solve it as two independent electrons, and that is the solution which has been shown here, except that in this particular case the spins of the two has been considered, and alpha and beta represent the plus and minus signs, or the circular right circularly rotating versus left circularly rotating electron spin, which is being combined here to the wave function to give it the total wave function. So, whenever a total wave function is given for a multi-electron system, the individual spins of the electrons are also to be considered, and that is what is being done here. Alpha beta, so the spin of one alpha and the spin of the other beta is being considered, and the possibility of one being of one kind and the other and their linear combination is something which is being looked at. And since the spin function due to Pauli's exclusion principle is antisymmetric, so when you change sign, so when the spin flips for one to the other, the sign changes, and therefore we have this antisymmetric relationship between them. So, this model includes the Pauli's exclusion principle in terms of the spin. Now, finally, we also looked at some problems which were just looking at if it was possible to understand how the energy transfers was being looked at. So, it is a very simple question which asks as to if there are only two energy levels separated by, say, the ionization potential of an hydrogen atom, which is 13.6 electron volt, what should be the wavelength of the laser in nanometer that can match this energy gap. Now, this has been asked because it is sort of like unit transformation, and the simple equation in this case is to recognize that the energy can be written in terms, in many different terms and units, and this is one of the ways of looking at it. Now, this is under the condition that this is all under vacuum, where the velocity that we are considering is the speed of light in vacuum, and therefore, this is written in this term. Typically, if it is matter is involved in this, then a refractive index term will come into the picture, but as of now, if you consider the simplest possible case, then the lambda can be simply calculated in this form, which turns out to be 91.8 nanometers. And so, this after this mathematics, this is what it comes out to. Now, after having done all of this, I also realize that it is time perhaps that we look at how to solve the hydrogen atom to at least some level, so that all these understanding is put to in the right place. So, the hydrogen atom is the simplest physical system containing interaction potential that is not just an isolated particle. Before coming to the hydrogen atom problem, we basically solve our Schrodinger equation problems in terms of particle in a box or rotating system, rigid rotor or simple harmonic oscillator. In doing so, we basically ensure that we are looking at potentials which are independent, and they are not interacting potentials here. Hydrogen atom is a complete problem in some sense, and it is also a good problem because it can be solved completely using the Schrodinger equation. So, that is the reason why we can look at it. And so, it is a simple one proton, one electron, and the electrostatic Coulomb potential that holds them together. It is a simple enough problem. The potential energy in this case is just E squared over 4 pi epsilon naught r. The attractive potential between the charges of the proton and the electron is separated by a distance r. So, it is all Coulombic, and this is a stationary state potential with no time dependence. We could just plug it into the Schrodinger's equation, time dependent equation, to get the form as it has been shown here. The potential looks quite simple, but it is a function of radial part r and not of x or x y z. So, what can we do about that? So, what we have to do is we have to recognize that we have to actually use the radial potential, means we are going to use use this in this form, where we have to put back the x y z in this form, and we will need to use the help of symmetry of the problem to use our mathematical approach. The spherically symmetric potential in this case tells us that we can use spherical polar coordinates, just like what we have done for 3D rigid rotor for instance. The only difference is here it is not a rigid rotor, the r can also change. So, as before we can look at it and define the volume element as r squared sin theta d theta d phi dr, and in the spherical polar coordinates r is the length of the radius vector from origin to the point that we are looking at in x, y, z dimension. Theta is the angle between the radius vector and the z plus axis, and phi is the angle between the projection of the radial vector onto the xy plane and the plus x axis. So, phi is tan inverse y over x. The equations on the preview slide tells us how to express r theta phi in terms of x, y, z. We can also express x, y, z in terms of r theta phi. So, we can take advantage of that and we can write it out in the individual terms, and then we can rewrite the 3D Schrodinger equation in this form, where it is a function of x, y, z, the energy. In 3 dimensions and in spherical polar coordinates we can rewrite this, because we know how to convert Cartesian coordinates into spherical polar coordinates in this form as we show here. Now, if we plug in our potential V, which we had discussed before, and multiply both sides by r squared sin squared theta, we get this form. Now, this equation gives us the wave function psi for the electron in the hydrogen atom. If we solve for psi, in principle we know everything that is to know about the hydrogen atom. So, that is the main part about it, because it is a one electron system and that is what it is. So, when we solve the Schrodinger equation in one dimension, we found out that one quantum number was necessary to describe our systems. For example, in the Bohr atom the electron moves in an orbit, but we need only one parameter to specify its position in the fixed orbit. So, we need only one quantum number. Here in 3 dimensions and with 3 boundary conditions, we will find that we need 3 quantum numbers to describe our electron. So, this is what we are getting to. So, we are really solving Schrodinger's equation for the electron in the hydrogen atom. However, we talk about solving the hydrogen atom because our solution will provide us with much more of what we need to know about the hydrogen. That is because for one electron system, Coulombic interaction, one you know particle, then you have essentially solved the whole thing. So, in order to solving linear algebraic equations, as we have been talking about, solving coupled algebraic equations, for example x, y together, and solving linear differential equations and solving coupled differential equations, example with derivatives mixed together, that is what we have in this case. So, we need to separate the variables. We have a coupled linear differential equation to solve. Maybe if we are clever, like when we were doing with the earlier calculations in some cases, we can make the problem easier. A big improvement would be to uncouple the variables. Stated more mathematically, when we have an equation like the one that we are discussing, we would like to see if we can separate the variables or split the equation into different parts with only one part of variable in each part. So, our problem will be much simplified if we can write the wave function, which is a function of r theta phi, in terms of 3 different functions: r, which is dependent only on r, theta, which is capital theta, which is dependent on the angle theta, and capital phi, which is dependent only on the phi. So, that is what we are after. So, let us assume that it is possible to break it up into these parts and see what happens. If our assumption works, then the orderly world of mathematics, we know that it will be right. So, we can rewrite this the original expression in this form, 3 different forms where we have taken them. So, with this assumption, the partial derivatives in the Schrodinger equation become like this, where the partial derivatives become full derivatives, because now they depend only on each coordinate at one point of time. To separate the variables, what we need to do is to plug in the wave function into the Schrodinger equation and divide by them, assuming that they are non-zero, and the result is what is now shown here. Once we do this, it immediately separates the phi variable, and the term 1 over phi d squared phi d phi is a function of phi only. So, let us put this over to the right side of the equation, and this gives us this form, where we have already separated out the phi part. So, this equation it has the form f of r theta, which is equal to g of phi. F is a function of r and theta only, while g is a function of phi only. So, how can this be? That's the natural question which may sometimes arise, that the right hand side only has phi in it but no r and theta, whereas the left hand side only has r and theta in it but no phi, and yet left hand side and right hand side is equal. This is only possible, so only one way, when you have a constant independent of r, theta and phi, which is equivalent to g of phi. So, does that mean everything is just a constant? That is not true. It just means that the particular combination of terms on the left hand side happens to add up to a constant which is the same as the constant given by the particular combination of terms in the right hand side. So, when we use this idea that the left hand side has this kind of a form, then we can write it in this kind of an expression where we have equated both the sides to a constant. Now, this is really good because we have taken one nasty equation in r theta phi and separated out into two equations, one in r theta and the other one in phi only. So, now the question is, can we actually separate out the r and theta part also? So, in order to do that, let us examine that. It turns out that although we do not want to do the detailed math here, that the constant has to be a square of an integer. So, this particular constant that we are talking about has to be a particular constant, like it has to be a square of an integer, and once we do that, then these equations would have solutions, otherwise there are no solutions. Now, this hunch we get from the fact that our left hand side is already well defined and well known. So, we can write our right hand side equation of this. It turns out that we will not do the math here, but the constant has to be a square of an integer. If not, our differential equations have no solution, and we already know that the right hand side of the equation therefore can be written simply as a part which is equivalent to a square of a constant, and it's I am highlighting the fact that the m actually depends on L with the lower subscript. So, where did this m sub L come from? It is an integer and we just happen to give it that name. The left hand side of our big Schrodinger equation also must be equal to ml squared now. So, if we set the left hand side equal to ml squared divided by sine squared and rearrange this, we get this kind of an expression. Once again, we have separated the variable. The left hand side is a function of r only and the right hand side is a function of theta only. Again, the only way to satisfy this equation is for the left hand side is to be a constant which is equal to a right hand side. The solution of this resulting differential equation will result in restrictions of this constant. In this case, the constant must be equal to an integer times the next larger integer, and that is one of the tricks that we find out as to how it is happening. And so, what we find is that we have taken our initial differential equation and split into three. Here are the three pieces rewritten slightly differently. The first two parts are the angular equations, where the double derivative of the phi function is a constant square, as the second part is basically a part where the constant was L times L plus 1, which we have utilized to write the second part, which is our theta variable, and finally the radial part is dependent only on the r function, and that is where we get the Schrodinger equation has been separated into three ordinary second order differential equations, equations 1, 2 and 3, each containing only one variable. Now, the solutions need to be found for the boundary condition, and we no longer need to be dealing with partial differentials because everything now falls into place by boundary conditions, that the wave function amplitude need to go to 0 at infinity and that they need to be single valued and so on and so forth. So, with this background, then the different parts of the equation can be solved. The radial part of the equation is called the associate Laguerre equation, and the solutions are that satisfy the appropriate boundary conditions are called associated Laguerre polynomial. Assuming that the ground state has L equal to 0 and that requires m sub L equal to 0, the equation 3, which is the radial part, becomes it takes this form, where the derivative of the r squared r dr yields two terms, which is based on the product rule. Writing those terms and inserting the spherical electrostatic potential, we get the final form, and we can then try a solution which is of the form a to the exponential minus r over a naught. A is the normalization constant, a0 is the constant with the dimension of length. On inserting the first and the second derivative of r, we are able to make the expression look much better, and given the condition to satisfy for any of the r is, for each of the two expression is in parenthesis is to be 0. So, we can set the second parenthesis to be 0 to solve for a0, which happens to be the Bohr radius as we find it here, and then we can set the first parenthesis equal to 0 and solve for E, which is what we get. Many often ignore the reduced mass confinement because it turns out to be essentially the mass of the electron. The difference of mass is so small that it is the smaller mass which comes. But both are equal to the Bohr results, and which are backed by the spectral lines. So, the hydrogen atom radial wave functions of the first few are now that we have seen them, we can write some of them from the books. So, you can see it in any of the books around, and these subscripts specify the values of n sub L, n and L, and these are the associated Lagarde polynomials. They are already normalized. Similarly, some of the associated Lagarde polynomials are given here with respect to the P, L, m sub L. L and m sub L are constant, which were used to separate the Schrodinger equation in the spherical coordinates. They were cleverly chosen and will become quantum numbers eventually. That is what the whole story is about, and for general cases these are to be normalized for usages. Solutions to the angular equations are given in this form as we have talked about. The product of the solutions of the angular and the azimuthal equations can also be found from the other part of the two expressions, which turn out to be, as I mentioned before, the spherical harmonics with which we started the whole problem, and these grouped solutions can be given into two functions, and they can be normalized and looked at in this form, theta and phi dependent spherical harmonics. The solution of the angular and azimuthal equations therefore give rise to the entire full picture. The radial wave function r and the spherical harmonics determine the probability density of the various quantum states. The total wave function psi r theta phi depends on n, L and m sub L. The wave functions therefore become a product function of the two cases, the radial part as well as the angular part. There are therefore two types of quantum numbers, radial and angular. The appropriate boundary conditions leads to the following restrictions on the quantum numbers L and m sub L. L can take any values going from 0 to L as long as it is less than n. M sub L can take any values from minus L through 0 to plus L, and mod of m sub L should be less than equal to L. So, the predicted energy levels are only dependent on the principal quantum number n with a lots of degeneracy, E of n equal to minus E naught over n squared. So, basically they are n squared degenerate. When n is greater than 0, for hydrogen atom n is always greater than 0 and it is an integer. All quantum numbers can become very large for very highly excited state. Transition to classical. N can take any values from 1 to any integer, all large values are possible. All quantum numbers can become very large for very highly excited states, and which can transit to the classical physical conditions. The principal quantum number n is critical in terms of defining the energy, because only r radial part includes the potential energy V of r. The result of this quantized energy is E of n minus mu over 2, this form, which is equivalent to E naught over n squared, which is just like what was predicted in Bohr's model. The negative sign means that the energy E indicates that the electron and the proton are bound together. As the energy only depends on n only, there will be a lot of degeneracy due to the high symmetry of the potential. A 3D sphere has the highest symmetry, and that is possible in 3D. The orbital angular momentum quantum number L and the spectroscopic notations can be also looked at in this same vein as we are now doing this. The letter names are given for the various L values when the reference is to an electron. So, the L sub value of 0 is letter notation is S, 1 is P, 2 is D, 3 is F, 4 is G, 5 is H. The electronic states are referred to by their N and L. A state with N equal to 2 and L equal to 1 is called a 2p state. The boundary conditions require that N is always greater than L. When referred to the hydrogen atom, we therefore have SPD kind of the shells, and the spectroscopic notation involves the capital SS, whereas the orbitals are always represented by the small letters. The spectroscopic notations for the atomic shells and the subshells are, as we have been showing here, has been given in terms of K, L, M, N, O, P, whereas the shell symbol has been given as SP, D, F, G and H. So, in summary, the quantum numbers which we have used are the three main ones, which is principal quantum number, orbital angular quantum number, magnetic quantum number m sub l. The boundary conditions of the wave functions to go to 0 at x goes to infinity result in n values can go anywhere, can take any integer 1 to n. L can go from 0 to n minus 1, m sub l can go from minus l through 0 to plus l, and the restrictions for the quantum numbers are such that n has to be greater than 0, L has to be less than 0 and less than maximum is n minus 1, m sub l mod is less than equal to L. With this summary, let us sort of finish on the idea of the hydrogen atom, because anything more than this would require the solution to the relativistic part of the Schrodinger equation, which we are not doing. The idea of the spin was introduced by Pauli in a different manner of symmetry, and which we will be looking at later. So, the final question in the problem that we are looking at in week 2 was concerning the approximations that are very importantly done, are very useful, and so this is what the statement was being discussed. The common and contrasting factors for the Born-Oppenheimer approximation and the Frank quantum principle are tested in terms of true false, which is what is being talked about. Born-Oppenheimer is for molecules, where Frank quantum is for atoms. Now, the fact of these are, the fact is not true, because as we will. So, the more important part to realize as a questioning of this is to revisit the idea of Born-Oppenheimer approximation and the Frank quantum principle, which we will just now do. But let us read through the problem which have been looked at, which is that Born-Oppenheimer is for generating molecular orbitals, whereas Frank quantum is for spectroscopic transitions. Both rely, which is a true statement, both rely on the fact that the nuclear mass is extremely large compared to that of the electrons, which is also true, and both are gross approximations and mostly fail is a wrong statement, because amazingly these two approximations work wonderfully truly for most of the time. And so, the basic point of these two approximations are that in quantum chemistry and molecular physics, the Born-Oppenheimer approximation is the assumption that the motion of the atomic nuclei and electrons in a molecule or an atom can be separated based on the fact that the mass difference between the two is extremely large, which means that the motion of the electron is extremely fast as compared to that of the molecule. And so, the separation of variables that we just discussed in terms of the hydrogen atom is in fact true due to the Born-Oppenheimer approximation. The Frank quantum principle, on the other hand, is the transition condition for any spectroscopic rule, and as we have been discussing, the both were discussed in this particular lecture in both same token. And this is a rule in spectroscopy and quantum chemistry that explains the intensity of vibronic transitions. Vibronic transitions are simultaneously changing the electronic and vibration energy levels of a molecule due to the absorption and emission of a photon or the absorption of energy, and therein it can only occur through vertical transition. That is because once again the nuclear coordinate motion is extremely sluggish as compared to the motion of the electrons, and that is the basic idea behind all of these studies that we have been discussing until now, and they form the basis of most of the implementation aspects in quantum computing and quantum information processing that we are actually dealing with in this entire course. And therefore, I thought it was extremely important that we revisit and understand these basic concepts once more to make sure that whatever we are discussing currently in terms of implementations do not become faded because of the logical understanding, and these things are not very clear. With this, let us end the lecture today, and I look forward to meeting you in the next one. Thank you.